This video is entitled Exponential Functions, Differentiation, and Integration. More specifically, we're dealing with the natural exponential function e. The next section after this video is addressing more all cases of exponential functions such as 2 to the x or 3 to the x or something like that. But this is only dealing with specifically the natural exponential function e to the x, which e to the x is the inverse function of natural log of x. So that means the statement y equals f equals e to the x if and only if x equals natural log of y. And then by using the relationship here of how inverse functions work, ln of e to the x is x, and e to the ln of x is x. And that's how you know something's an inverse. It's 1-to-1, and you get this x relationship. Now e, you don't have to actually know this number, 2.718, blah blah blah, as far as the value of e. Now, here's one way that e is defined. E is 1 plus 1 over n raised to the n as n goes to infinity. So it's never a precise value. It's just you achieve more and more accuracy to it the larger and larger n gets. And in fact, we will in Cal 2 see how this limit is that's what we're saying right here, as n goes to infinity can be written as a limit. We'll be able to derive this limit and show that it does equal e. And here I just have a graph of e to the x and ln of x, and remember from the section on inverse functions that they are in the mirror image across the line y equals x. So now I'm not that much concerned about the algebra of this like you would have been possibly in algebra class or pre-cal, but just wanted to show you a couple of these as a refresher. We're more interested in the calculus with the derivatives and the antiderivatives. But let's say you're trying to solve an equation like this, e to the x plus 2 equals 7 for x, and you're trying to get that x to come down, you apply natural log both sides. So that, in other words, natural log basically eliminates the e and leaves you x plus 2, then you have natural log of 7. So technically the exact answer to this question is -2 plus natural log of 7, or then as a decimal, there's a three places approximation. And just the opposite, if you're solving a natural log equation, this one, natural log of 2x plus 5 equals 3, if you apply e, now not multiplied, it has to be e raised to that. So e raised to both sides. So that will kill the ln, you're left with 2x plus 5. So it's not 3e on the right side, it's e cubed. And then it's pretty easy to solve from there. So it's e cubed minus 5, all divided by 2 would be the exact answer. As a decimal, it's roughly 7.543. The derivative of the natural exponential function. The derivative of e to the x equals e to the x. No, that's not a typo. That's exactly right. And then the derivative of e to the u is e to the u du dx. So yeah, that's a pretty straightforward rule. You don't have to even worry about subtracting from one from an exponent or anything. And it doesn't get much easier than that. The derivative of e to the x is e to the x. If it ain't anything other than exactly x, you'll have to do a derivative of whatever that exponent is. And I used, because it was a lot quicker, just to show you this, I did a proof using logarithmic differentiation. I've also done proofs using the limit definition from the limit of f of x plus h minus f of x all over h as h goes to 0. You can derive this that way too. That works. But this one's pretty quick and straightforward. So I start with y equals e to the x. I use logarithmic differentiation, so I natural log both sides. Now when I natural log the right side, ln of e to the x, I'm just left with x. And as we've seen before, the derivative of ln of y is y prime over y equals 1. Bring the y over, so you have y prime equals y. And then We know what y is from the very beginning. You substitute it in there. It's e to the x. So therefore, when y equals e to the x, y prime equals e to the x. All right. So let's just look at some examples of the derivatives of these. Yeah, I think shouldn't find these to be too bad, I don't think. Oh, let's see. How about the derivative of e to the x cubed? Well, automatically, you see from up here, the e to the u du, doesn't matter whether you put it first, but I did, but then I rearranged it over here and put it at the end. But anyway, what I'm trying to say is when you're taking the derivative of e to the something, that e to the something will be part of your answer. So you notice there's no subtracting 1 from the exponent to bring anything down. So you automatically, e to the x cubed is part of your answer, and then the rest of your answer is taking the derivative of that x cubed, which is 3x squared. And I just moved it in the front because I thought it looked better, especially with the 3. I just thought it had a better appearance that way. But it's not wrong to write it at the end. So really, it's not too bad. Just take the derivative of that exponent and attach it to the original function. So e to the negative 7x, it would be e to the negative 7x times the derivative of negative 7x, makes it negative 7e to the negative 7x. And this makes me think of sometimes if you ask a student learning this, what's the derivative of just e to the negative x, like that? Sometimes people will say, oh, it's just e to the negative x. Well, no, that's not quite right. When it's e to the positive x, that's true. That's because the derivative of positive x is positive 1. But the derivative of negative x is negative 1. So actually the derivative of this would be negative e to the negative x. Oh, wow. All right. And this is sometimes a fun one to do in class if I don't already have the answer there. Doing a face-to-face class, let's show, hey, what's the derivative of e to the third? And it'll be interesting to see what people's answers might be. But it's 0 because you said d dx and there's no variable there. No variable. E to the cube is just a number. So you're just taking the derivative of a number, which would be 0. Or if you wanted to get real fancy, you could say, well, the derivative of e to the cubed would be e to the cubed times the derivative of 3. Well, the derivative of 3 would be 0, and it's still 0. So so the 0 takes out that e to the cube that would be there. So, but actually the simplest way is just realizing that it was a constant. So that's the end of it. All right, let's see what I did here. E to the negative 3 over t squared. For these kind of problems, I like to get it out of fractional form. So I just rewrote it like this. Wrote it as negative 3 and then brought the t up and made it negative 2. So then we're just basically, so I wrote it like this. So it's, this time I went ahead and stuck the original function at the end and did this, which that's fine. Obviously, you can do it the other way, but I went ahead and did, so this is the d dt of the exponent right here times the original function. So the derivative of this negative 3 t to the negative 2 would just be 6t to the negative 3. And then times the original function. So that's it. And then here I wrote right below it what it would be, if you rewrote it back as positive exponents. I'm not saying you have to, but if you did, that's what it would look like. All right, here's one that's going to be a product rule. X squared times e to the negative x. So I just kind of wrote the product rule there. And so we've got f prime, the derivative of x squared will be 2x times g, which is e to the negative x, plus x squared, and then which I've already explained a minute ago, the derivative of e to the negative x is actually negative e to the negative x. Here I just have it written like this. And then you can put the minus out in front there, just so it looks a little better than that. So then you just have 2x e to the minus x squared e to the minus x. That's good enough, but in case you were wondering, yes, you could factor out an x, and you could also factor out an e to the minus x. Let's see. So how about if y equals e to the sec x? Well, this one's no problem. As long as you know the derivative of secant x, then it's no problem. We have e to the sec x times the derivative of sec x, which is sec x tan x. So y prime equals e to the sec x times sec x tan x. Here's a quotient rule. For this one, so you take the bottom, which is e to the 2x plus 1, times the derivative of the top, which the derivative of e to the 2x would be 2e to the 2x, because the derivative of 2x is 2. Minus, for the quotient rule, the top, e to the 2x, and then times the derivative of the bottom, which is the same as the derivative of the top, because the plus 1 has no effect. So it's still 2e to the 2x, over the bottom squared. And I just cleaned up the numerator a little bit. I probably necessarily didn't have to, but I mean, because a couple terms canceled, so it worked out real nice. So clean that up, so you just end up with this 2e to the 2x over e to the 2x plus 1 squared. Now this next one's interesting. This brings back that second fundamental theorem of calculus that we learned before. Some people really struggle with this idea, but it's not very complicated, so I'm not sure why they struggle with it. Maybe they think because it's actually easier than what they think it's going to be. I don't know, but you can go back and see that. That's, and I'm not sure which section number, but it's in one of the integration sections. So it's the one that you would find the definite integrals in, because that's the regular first fundamental theorem of calculus, how to evaluate a definite integral. This is the second. But all you have to do on these kind of problems is you're not actually integrating anything, but to take the derivative of this integral, the process involves just substituting whatever this upper limit is, because assuming the bottom one's constant, which it will be, it would actually be subtraction if it wasn't, but if it's assuming there's just any kind of 0, 1, whatever on the bottom, you put the e to the 2x in for the t, and then you take the derivative of e to the 2x and tack it on there. So you see, all I did was put e to the 2x in there for t, which is natural log of e to the 2x plus 1, then took the derivative of e to the 2x, which is 2e to the 2x. So that's it. That's all that's involved. No integrating, no anything. Just a matter of substituting and then taking the derivative of that exponent. All right, now we're going to go back to something we learned a long time ago, how to find the equation of the tangent line, but we're just going to apply it now to a derivative involving e. So let's see what this is all about. As long as we get our derivative, this won't be too difficult. So there's our function, y equals e all raised to the negative 2x plus x squared at the point 2, 1. So we need the derivative to get our slope. So I went ahead and put the derivative of the exponent first, and you see the original e is going to be in there, obviously. And then the derivative of the exponent goes in there. So the derivative of the exponent would be negative 2 plus 2x. And then so there's our derivative right there. And now all we have to do is put 2 in there for x. We'll get 0 up here because we'll get negative 4 plus 4. And we'll get 2 here. So we get 2e to the 0. E to the 0 will be 1. Any number that's not 0, that's called indeterminate when you have 0 to the 0, indeterminate form. Talk more about that in Cal 2. But e to 0, e is a number, so e to the 0 would just be 1. So it makes that slope equal 2. So that means that derivative 2, see, so this 2 right here for the 2x is not coming from the x. It's coming from right there. So your slope is 2, so we know we're starting at y equals 2x plus b at 2, 1. So now I put 2 in for x. I put the 1 right there in for the y. Solve for b. I get b equals negative 3. And then I have y equals 2x minus 3. So just for grins, I kind of graphed them there, and there's 2 1s about right there. Well, okay, that tangent line then looks pretty good at that point. So I like it. Main thing is, it's not like cutting through some weird direction. It's just kind of clipping it right there at that point, like a tangent line's supposed to do. So right here's something, bring something back we've learned before. Implicit differentiation. Let's see how we fare with this here. So remember that's the process that, of course, you're taking the derivative with respect to x. But every time you take the derivative of any y term, you have to tack on a y prime in there. I use y prime. Some authors may use dy dx, which obviously is fine, or some instructors might prefer that notation. I just use y prime just because it's quicker and easier to write than dy dx. That's the main reason. So we have the idea that so the e to the xy will be e to the u du, basically, which I didn't take the derivative yet of this, but I set it up, so it's e to the xy times whatever the derivative of xy will be, which will take care of the next step. Now the next part will be, we'll take the derivative of the x squared, and then we'll take the derivative of the y squared, and then the derivative of the 10. So I'll work my way the other way. So that's going to be 0 on the right side. But anyway, we'll come back over here. So x times y has to be treated as a product rule. So I did f prime g. So the derivative of x is 1 times g, which is y, plus f, which is x, times the derivative of y, which is 1, but it's 1y prime. You have to put the y prime in there. So every time you differentiate a y, you have to put a y prime. So look at this next term. d dx of x squared would just be 2x. But then the derivative of d dx of y squared is 2y, but it's 2y y prime. So now essentially the calculus is done. The rest of this is just algebra. You need your y prime terms to be on one side and your non-y prime terms to be on the other side. So, well, first of all, though, I did just distribute here. Okay, let me mention that. I distributed through that bracket, parentheses, whatever you want to call it there, to get this. Then we group them. So I left the two y prime terms on the same side and then moved the two non-y prime terms to the other side. Because the idea is once you do that, you factor out a y prime, which I did right here. And then when you factor out a y prime, you divide both sides by what you factored out. So we end up with this negative y e to the xy minus 2x divided by what we factored out, which or left after we factored out y prime, which is x e to the xy minus 2y. Now, if you look at my answer, my answer versus the maple answer, my answer might not look right. But it is, because I'm sure I mentioned this when I did the implicit differentiation video, but if I didn't, I'll say it now, is that, it all depends on which side you put the y primes on. But the reason why, now you see these basically have the same terms, as the y, e to the xy, 2x, x e to the xy, and 2y. But you see all the signs are opposite, negative, negative, positive, positive, positive on bottom, negative, and then negative, positive. That's good. That's what I want. If they're all the opposite, that means both of these answers are correct. They're just in different forms, meaning you could take either answer and multiply it by negative 1 over negative 1, which is just a fraction that's equal to 1, and you'll get the other answer. So that's always key when you're doing implicit differentiation, is just if you get an answer and think, wait, all the signs are opposite from my answer choices here. Well, that's good. If they're all opposite, that means pick that answer, because that's what you're looking for. All right, so integration rules for the natural exponential functions. Well, if the derivative of e to the x is e to the x, I think it makes sense then that the antiderivative of e to the x would be e to the x plus c. And then, of course, a lot of times we'll have e to the u, which will be e to the u plus c. So this is not always going to be true, and you'll see an example of this here in just a minute. But the thought process on this when you're doing u substitution for the e's is the first thing you want to look for is u going to be the exponent? Well, if it's going to fit e to the u, it has to be, but there are some exceptions where there's some integrals that have e, but then yet that's not the case. So so let's look at this one. It's x cubed times e to the x fourth. So you let u be x to the fourth. That way du would be 4x cubed, and then divide both sides by 4, so you have 1/4 du equals x cubed dx. So see, your 1/4 du then takes care of the x cubed and the dx, and this part here in the middle, that's just going to be e to the u. So you end up with 1/4 integral of e to the u du. I think once you get to this part, I think it doesn't get much simpler than e to the u du. It's probably the simplest antiderivative you can have, because you don't have to worry about doing the plus 1 over the plus 1. It's just going to be e to the u. So e to the u will be e to the u. I like that. And then replace u with what u is. So then your answer will be 1/4 e to the x fourth plus c raised to the x fourth plus c. All right. So I'm not going to worry about going through this alternative method. I wouldn't necessarily recommend doing it that way, but I just wanted to show that to you. I think the other way is better, but I wanted to show that. Well, let's take a look at this one. And I like to take these kind of things that are fractions, and both with these next two problems, is get rid of every fraction, meaning that move the x cubed up to make it x to the -3, and get rid of the fraction of the exponent here, e to the 1 over x squared. Rewrite that as x to the -2. Because if you look at it in this form, you might look at that u being that exponent. Well, how is this x squared going to produce this x cubed? Blah, blah, blah. Well, yeah, it doesn't look logical. But as soon as you do this, it works. Then it makes more sense. So then you let u be x to the -2, and then du would be -2x to the -3 dx. So there, now that's how you're getting your x to the -3 right there. And that will give me -1/2 du equals x to the -3 dx. And there we go. So you can see what I wrote in red above the integral. So the first part's obviously e to the u, but then the rest of that would just be represented as -1/2 du. And there we go. So once you get into that form, that's the key. So then you have -1/2 e to the u du, which of course will be -1/2 e to the u, which then becomes -1/2 e to the x to the -2 plus c, which of course you could rewrite that as 1 over x squared in the answer if you wanted to. There's no need to, but who knows, on a multiple choice question that might be required. Same thing with the square root of x's. You bring the bottom square root of x up and make it x to the -1/2. Then you just rewrite the exponent there as x to the 1/2, and you have u equals x to the 1/2. Take the derivative, it'd be 1/2 x to the -1/2. We divide both sides by 1/2 or multiply by 2. Either way you do it, you're gonna get 2 over here and cancel the 1/2. So 2 du will equal this x to the negative 1/2 dx right here. And then we have it. So we have 2 e to the u du, which becomes 2 e to the x to the 1/2 plus c, or, you know, the answer might have the square root of x back in there as the exponent. Either way. Next example. Not too bad, as long as you realize that you know what the derivative of cotangent of x is. The derivative of cotangent x is negative cosecant squared, so we just have to adjust for a negative, which I did right there. I didn't bother to write a whole other line where I just moved the negative over here, but I think you'd have figured that out. So basically it's just negative e to the u du, so it's negative e to the cotangent of x plus c. Very good. Now here's one where I was talking about where we have e in our integral, but this time the use of u as the exponent will not make any kind of sense in this problem. The only thing that's going to make sense here is to let u be the entire denominator. You know, once again, I've mentioned this in other videos, is that there's no chance you can have du ever end up on the bottom. So u can be on the bottom, but du can never be on the bottom. So you let u be 1 plus e to the 2x, and that's good because that'll give you du equals 2e to the 2x. And then divide both sides by 2, so that gives you 1/2 du equals e to the 2x dx. Perfect. And then that means your numerator will be 1/2 du. So let's put the 1/2 to the outside. There's your du. And we have u on bottom. So even though we have, you know, e's in our problem, the integral is actually not going to turn out being an e result. It's going to be a natural log because it's du over u. So we end up with 1/2 natural log of the absolute value of u. So we have 1/2 natural log of the absolute value of 1 plus e to the 2x plus c. So like I said earlier, that, you know, when you look at an integral involving e, first place you want to check, you should check, is the exponent as your being your u here. But this is totally different. This one we had a e's in there, but then that wasn't an e integral. It turned out being a natural log with e in the answer. Now the next one, I won't go through all the steps because it's pretty much the same thing. But you see how I have a cube right here in the bottom. The reason why I did this is because, and I know I mentioned this in the natural log section on integration, is that sometimes people will just see du over u to the anything, and they'll kind of mistakenly call it natural log every once in a while. But that's not true. It's only when it's du over u to the first power on bottom, which means it's u to the negative 1. That's natural log. Anything else? Power rule. Bring that up. U to the negative 3. So then you just do the power rule. U to the negative 2 over negative 2 with a 1/2 there. So you get 1/4, negative 1/4, excuse me, u to the negative 2, and substitute it back in there. So you have negative 1/4, 1 plus e to the 2x raised to the negative 2. Okay, so very good, very important that we don't automatically call any u on the bottom natural log unless it's u to the first. All right, so let's see what we have here. Now, for basic integrals involving just e to the something times x, and you can actually, it's probably good just to learn these without having to show too much work. In fact, I could go into more detail about that in Cal 2 because we use these in other contexts, but you could save yourself a lot of effort if you just learn that e to the ax, where a is some coefficient, dx equals 1 over a e to the ax. So we saw earlier, like the derivative of e to the 6x would be 6e to the 6x. But the antiderivative of e to the 6x would be 1/6 e to the 6x plus c. So you see, for this one, I worked it out to show you that that ends up being true, but the point is you don't have to do this every time for these basic ones like this. You can just kind of know that, and then you're in good shape. So yeah, so I worked it out using formal substitution, but to guarantee it, which I could have done. I could have done it just using u equals ax and just shown it in a general form and got this answer, but I just specifically chose an answer with a being a numerical value. In this case, it was 8. All right, here's a little fractional problem. We have to do division, not long division. I wouldn't have to do long division on this, but just when you see a bunch of terms on top and one term on bottom, it's just going to be term by term division. So we take e to the 2x divided by x, 2e to the x, 2e to the x divided by e to the x, and 1 divided by e to the x. Excellent. So e to the 2x divided by e to the x, you subtract exponents, so 2x minus 1x would be x. In this case, the e to the x is canceled, so you have 2. And then 1 over e to the x is e to the negative x. And then pretty easy from here. Antiderivative of e to the x will be e to the x. Antiderivative of 2 would be 2x. And then the antiderivative of e to the negative x would be negative e to the negative x. You can think it's the same as the derivative, but actually you can think of it as being your a is negative 1. So 1, using this right here, 1 over negative 1 would be negative 1. So it's negative e to the minus x. Excellent. Let's see what we have here. Here's another good example of an integral that has e's in it, but yet the exponent of e will not be the u. In this case, the u will be all e raised to the 2x, not 2x. It needs to be e raised to the 2x. And the main reason for that is because, like I said, you tried something that didn't work, try again, but that way the derivative of this e to the 2x right here in the parentheses will give you an e to the 2x right there. Specifically, the derivative is 2e to the 2x. So we just have to adjust for the 2 to make it 1/2 du equals e to the 2x dx. So essentially then you have to take care of that. So the e to the 2x dx is now just 1/2 du. Then we have 1/2 cosecant of u du. So this comes from the formula sheet that we've learned in the natural log section on integration. The antiderivative of cosecant is negative natural log of cosec plus cotan. So it'll be the negative 1/2. Negative, well, 1/2 was here, but the negative comes from here. And then natural log cosecant of the u, which is e to the 2x, plus cotangent of the u, cotangent e to the 2x, absolute value of all that, plus c. So there you go. Once you kind of pick the right u, it's not too bad. This one's kind of interesting. It's got ends up not working out too bad, but it's a little busy looking, I guess you'd say, or a little congested looking, so it might be a little tricky on how to figure out how to get it started. I think the main thing you have to do is kind of ignore this last e to the 4x at first. We have to look at this as just involved in sines and cosines. And then as we've talked about before with these trig integrals, it's that if they're sine and cosine together, the u has to be the one that's if the exponent's other than 1. So this is sine cubed, so the u has to be sine. So u sine, of course the argument has to stay with it, so it's u of sine of e to the 4x. Well, the derivative of sine of u is always cosine of u du. So the derivative will be cosine of e to the 4x times the derivative. I went ahead and put an extra step here, e to the 4x. So the derivative of e to the 4x would be 4e to the 4x. So we divide both sides by 4, and then 1/4 du will be cosine e to the 4x times e to the 4x dx. So now you can see this little trailing e to the 4x here at the end was taken care of as part of du. So it wasn't something that we had to account for, by some other method or something like that. Because you look at, you see the sine, you see the cosine, you're going, hey, what's going on right there? No problem. So all of that turns into 1/4 du. And then this just becomes u cubed. So you let u be this, and then you put u cubed right here. The integral just becomes 1/4 the integral of u cubed du. Antiderivative u cubed would be 1/4 u to the 4th. So the 1/4 multiplied together make 1/16. So our final answer would be 1/16 sine to the 4th of e to the 4x plus c. Very good. Here's a definite integral. Where I let u be sec 2x, because that's knowing that the derivative is going to get you your sec tan right there. That's the clues, the derivative of secant and secant tangent. But we have to remember the 2 here, the chain rule. So the derivative of sec 2x is actually 2 sec 2x tan 2x. So we divide both sides by 2. And we get 1/2 du equals sec 2x tan 2x dx. So all this will be taken care of by 1/2 du. So now we have essentially 1/2 e to the u du, but this is a definite integral. So I'm going to change my limits of integration. So I'm putting pi over 2 in for here, the secant of 2x, and then pi over 3 in for there. And since calculator doesn't have those trig functions except for sine, cosine, and tangent, so to figure out what secant of 2 times pi over 2 would be, it would be 1 over cosine of 2 times pi over 2, gives you -1. Same thing here, 1 over cosine of 2 pi divided by 3 is -2. So I have 1/2, -2 on bottom, -1 on top, e to the u du. So which is the antiderivative would be 1/2 e to the u. Put in -1, put in -2. I think this is good enough right here. 1/2 e to the -1 minus 1/2 e to the -2. That agrees with my Maple answer. The only thing Maple did different was distributed the 1/2, and for some reason they put the e to the -2 in front, takes the negative sign right there. But that answer matches mine. It's just rearranged a little differently. Very good. Another definite integral. Let u be the exponent here, -x squared plus 2, which makes the derivative. 2 comes down, 2's will cancel. -x dx, so I'll move the negative, not the x, just the negative to the other side to make it negative du equals x dx. And then I'm changing my limits of integration, so I'll put in square root of 2 into -x squared plus 2, I'll get -1. Put in 0 here, I'll get 0. So I have -1 on top, I have 0 on bottom, I have a negative on the outside. And then I'm using this property of definite integrals right here, which you don't have to use, not required. I like using it because I like getting rid of those negatives. So anytime that you flip the limits of integration like I did here, you're creating a negative, which will then eliminate the negative that's there. So we have e to the u, -1 to 0, e to the u du, which will equal e to the u from -1 to 0. And then e to the 0 is 1, and then e to the -1 is just -1. So 1 minus e to the -1. This could be a fun one to put in Maple real quick, so why don't I? So we have zoom in. I'm already zoomed in. 0 root 2 x times e to the negative x squared divided by 2. Let's see what we get. Ta-da! How about that? We are that good. Snip it right out of here. Let's add it to the notes. All right, so very good. I'm going to show an example of extrema and points of inflection. I don't normally ask this on my exams. I guess I could reserve the right to bring it back. And maybe that's the reason why I would like to do this, in case I ever did in the future. As of right now, in 2017, I'm not doing it. But also, if other students from other calculus sections are watching this, and other instructors, and maybe their instructor is going to do it, so potentially this could be helpful for them. So let me just kind of run through this real quick. So here's one we're going to do, xe to the negative x. So product rule, so derivative of x is 1 times e to the negative x plus x, and the derivative of e to the negative x would be negative e to the negative x. So you'll have this result right here. Second derivative, the derivative of e to the negative x will be negative e to the negative x. And then we have, I guess I took the minus out right here and then did a product rule, so it's going to be derivative of x is 1, and you have e to the negative x. And then this is minus because when you take the derivative of e to the negative x again, you're going to generate another minus sign. So it's x minus times negative e to the negative x. I just put the negative there. Now I combine my like terms. A negative e to the negative x minus another e to the minus x would give me negative 2 e to the negative x. And then this minus and that minus makes plus for that term right here. So there are the first two derivatives. So let's see. Let's take the first derivative, set it equal to 0. So this time, normally I don't care about stuff like this, but this time we have to factor out this because we're setting it equal to 0. Normally you don't have to, but so I factor out an e to the minus x, and I get e to the minus x times 1 minus x, which you set both pieces equal to 0, e to the minus x equals 0, and 1 minus x equals 0, which clearly gives you x equals 1. And then here, this is interesting because you have 1 over e to the x now equals 0. Well, 1 over something can never be 0. We're not talking about a limit here. We're talking about an exact 0. So, so that's gone. That produces nothing. So 1 is the only critical number. Now, instead of doing a sign chart, what I did just to kind of bring back refresher here is I'm using the second derivative test for critical numbers. And you may recall that means if you take your critical number, which always comes from the first derivative, and you plug it into the second derivative and you get a negative result, that means you have a maximum. If you get a positive result, that means you have a minimum. So I plugged in this 1 into this second derivative right here and did all this and got a negative number. Therefore, I have a relative max at 1 comma f of 1. And which we could figure out f of 1 if we wanted to, but it'd be easy to put 1 back in there. Actually, it'd be e to the negative 1. F of negative 1 would be e to the negative 1. So now we're working to the second derivative. So I use the blue for the first derivative and the red for the second derivative. So same kind of idea. You're going to factor out another e to the minus x right here. And then you're left with negative 2 plus x after you factor negative 2 here, plus x there, negative 2 plus x. So once again, just like the explanation I gave up here, e to the negative x cannot be 0. Negative 2 plus x equals 0 gives you a solution, obviously. It gives you x equals 2. So let's see if this is going to be a point of inflection. We have to know, it's a potential point of inflection, but we don't know for sure unless the sign changes on the concavity. So I did a quick little sign. I didn't do this sign chart as formally as I did the ones in that section in my video and my notes. I just did a real quick thing here. So less than 2, greater than 2. I use test values of 0 and 4. Second derivative is negative. Actually, I should have done that. I was going to put it. Trying to move those numbers, but it won't cooperate. But I'll just do this, so for put a negative here and put a positive. It wasn't asking for concavity, but I'll just, so we're going from concave down to concave up. Therefore, we do have a point of inflection, so it's at 2f of 2. So there's the graph of the original function. So you can see that there's a relative max where the red dot is, and it starts decreasing, and it starts kind of coming back up again. It's very subtle, you can't tell, but it's concave down, it's decreasing, and then starts slightly, it's still decreasing, but the curvature of it starts bending slightly upward. That's what it is. It's still decreasing, but the concavity is upward. So it's concave down, concave up. There's 4. This is scaled by 2s here. I guess I could have put the scale there, but yeah, that first dot's at 2, and the second one's at 4. And there we go. So the graph does match it. Okay, that concludes this video on the natural exponential function, differentiation and integration.